We now talk about the mean value theorem, MVT. The proofs of many important facts in calculus depend on MVT. The statement of MVT is on screen. There are two conditions. The first condition is that the function is continuous on the closed interval from a to b. The second condition is that the function is differentiable on the open interval from a to b. Intuitively, the first condition means that the graph of the function has no breaks. The second condition means that the graph of the function is smooth. So that we can talk about the tangent line to the graph of the function at any point strictly in between a and b. To motivate the conclusion of MVT, now let's consider the tangent line to the graph of the function at all the points when the x-coordinate is in between a and b. This is the tangent line when x-coordinate of the point is very close to point A. If we change the point, the x-coordinate of the point from A to B, the tangent line changes as shown. The following observation will motivate MVT. Listen carefully. Intuitively, we can see of all these tangent lines, there must be a special tangent line, something like this, that is parallel to the secant line passing through these 2 points. Now let's recall two non-vertical lines are parallel if and only if they have the same slope. And the slope of the tangent line to the graph of the function at a point is described using the derivative of the function at the x-coordinate of the point. So the observation in terms of the slopes is stated as follows. If the two conditions are satisfied, there must be a number c in between a and b such that the derivative of the function at the number c is equal to the slope of the secant line. This is the conclusion of MVT. You see, the right hand side is the slope of the secant line passing through the 2 points. Is the change in y over the change in x. The left hand side is the derivative of the function at some number c. So the whole thing says if these two conditions are satisfied, then there must be a number c strictly in between a and b such that the derivative of the function at c, which is the slope of the tangent line to the graph of the function at the point when x-coordinate is c, is equal to the slope of the secant line passing through the 2 points. The second equation is equivalent to the first equation because if you multiply two sides of the equation by the non-zero number of b minus a, you'll have that equation. We have seen the geometric interpretation of MVT. MVT can also be interpreted in terms of rates of change. The right-hand side of the equation is the average rate of change of the function over the interval from a to b. The the left-hand side of the equation is the instantaneous rate of change of the function at a number c strictly in between a and b. So the statement of MVT in terms of rate of change is as follows. If the two conditions are satisfied, then there must be a number c strictly in between a and b such that the instantaneous rate of change of the function at c is equal to the average rate of change of the function over the interval from a to b. There's a very useful special case of MVT. It's called the row theorem. In addition to the two conditions, the function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. The additional condition is that the values of the function at the two endpoints are equal. If this condition is true, you can see in the conclusion of MVT, the numerator is equal to 0. The denominator is a non-zero number. So the right-hand side becomes 0. So there exists a number c strictly in between a and b such that the derivative of the function at c is equal to 0. We now look at some questions designed to understand the meaning of MVT. The first question is to verify MVT using that particular function on that particular interval. Now the solution. We need to verify the two conditions are satisfied, and also the conclusion of MVT is also satisfied. Since the function is a polynomial, the function is continuous and differentiable on any interval. And differentiable on the open interval from 1 to 4. So we see the two conditions are satisfied. So before we show the conclusion of MVT is true, we need to compute a few things. We need to differentiate the function. The derivative of the function equals negative 2x plus 6. The value of the function at 1 equals negative 1 squared, and then plus 6 times 1 minus 2. This number is equal to 3. We also need the value of the function at the right endpoint of 4. The value of the function at 4 equals negative 4 squared, and then plus 6 times 4 minus 2. Negative 16 plus 24 minus 2. This value is 6. Now to show the conclusion of MVT is true, we need to find a number c. A number c on the open interval from 1 to 4, such that the derivative of the function at c equals, look at the conclusion of MVT, equals the value of the function at b minus the value of the function at a. On denominator you have b minus a. In this particular case, a value is 1, b value is 4, equals on numerator you have the value of the function at 4 minus the value of the function at 1. On denominator you have 4 minus 1. This equation is equivalent to, that is, the derivative of the function at c, the derivative of the function at c is equal to negative 2c plus 6. On the right hand side, we need to compute the value of the function at 4, which is 6, minus the value of the function at 1, which is 3. 6 minus 3. On denominator you have 4 minus 1, which is 3. This equation is equivalent to, that is, negative 2c and plus 6 equals 1. So we need to solve this equation for c. The solution to the equation is going to satisfy the conclusion of MVT. Negative 2c plus 6 equals 1. The equation is equivalent to negative 2c equals, on two sides of the equation you subtract the constant of 6, you have negative 5. So c value is equal to 5 over 2. To verify MVT, you do need to make sure this value of c is indeed on the open interval from 1 to 4. 5 over 2 is 2.5 is indeed strictly in between 1 and 4. So this number is on the open interval from 1 to 4. Therefore, we have found a value of c in between 1 and 4 such that c value is 5 over 2. In between 1 and 4 such that the derivative of the function at c equals the value of the function at 4 minus the value of the function at 1 over 4 minus 1. This is the conclusion of MVT. So MVT is verified. The next question is designed for how to use MVT. Now the solution. We are going to apply MVT on the interval from 4 to 6. since the function is differentiable. At all the numbers, the function is continuous on the closed interval from 4 to 6 and differentiable on the open interval from 4 to 6. So we are going to apply MBT for the function on the interval from 4 to 6. By MBT, there is a number C on the open interval from 4 to 6 such that the derivative of the function at C equals the value of the function at 6 minus the value of the function at 4. On denominator you have 6 minus 4. This equation is equivalent to the derivative of the function at C equals, we are given the value of the function at 4 equals 5. The value of the function at 6 minus 5. On denominator you have 2. Now, since we are given the derivative of the function is always greater than or equal to 2 and less than or equal to 3, in particular, the derivative of the function at C is a number in between 2 and 3, greater than or equal to 3, greater than or equal to 2 and less than or equal to 3. We have, now remember that the derivative of the function at C is always in between 2 and 3. This means the right hand side is always in between 2 and 3. So we have the right hand side is always in between 2 and 3. In the given question, we are looking for the smallest and the largest possible values of f of 6. Now we can solve that inequality for f of 6. We multiply two sides of the equation by a positive number of 2. We keep the direction of the inequalities. So f of 6 minus 5 is greater than or equal to 2 times 2 is 4, and then 3 times 2 is equal to 6. And then we solve that inequality for f of 6. To do that, all we need is to add 5 to all these terms. So we have f of 6 is less than or equal to, greater than or equal to 4 plus 5 is equal to 9. On this side you have 9. On the right hand side you have 6 plus 5 you have 11. So you can see the largest possible value of f of 6 is 11. The smallest possible value of f of 6 is equal to 9. Actually, using the argument, we can see when the derivative of the function is equal to 3, when the derivative of the function at c is equal to 3, then the value of the function at 6 is 11. And likewise, when the derivative of the function is equal to 2, then the value of the function at 6 is equal to 9. So 9 is indeed the smallest possible value of f of 6, and 11 is indeed the largest possible value of the function at 6. So therefore, the smallest and the largest possible values of the function at 6 are 9 and 11 respectively. We now look at how MVT is useful for proving many important facts in calculus. On the screen, we let the function f of x be differentiable on the open interval. Now the condition is that the derivative of the function is equal to 0 at all the numbers or at every number on the open interval. Under the condition, we want to show that the function is a constant function on the open interval. By that we mean the values of the function at any two numbers on the interval are equal. Now proof. The idea is that we choose two arbitrary numbers on the interval from a to b. We want to show the values of the function at the two numbers are equal. So we let x1 and x2 be two arbitrary numbers on the interval from a to b. We can assume the two numbers are different and the one number is less than the other number. We assume that x1 is less than x2. Now we want to show the values of the function uppercase f of x at x1 and the value of the function at x2 are equal. We're going to apply MVT on the interval from x1 to x2. Before that, we need to verify the two conditions are satisfied. Now, since the function uppercase f of x is differentiable, on the open interval from a to b, the function f of x is continuous on the closed interval from x1 to x2. Now let's recall, differentiability implies continuity. If a function is differentiable at a number, then the function must be continuous at the number. And of course, the function is differentiable on the open interval from x1 to x2. Again, we wanted to apply MVT on the interval from x1 to x2. That's why we have to verify the two conditions. By MVT, there is a number C C is a number on the open interval from x1 to x2, such that the value of the function at x2 minus the value of the function at x1 equals the derivative of the function at the number C, and then times x2 minus x1. Again, we are applying MVT on the interval from x1 to x2. Now, you look at the condition. The derivative of the function at any number on the interval from a to b is equal to 0. In particular, the derivative of the function at c is equal to 0. This value is equal to 0. So we have the value of the function at x2 minus the value of the function at x1 is equal to 0. Right. Hence, the value of the function at x2 equals the value of the function at x1. So far, we have proved the value of the function uppercase f at any two numbers on the interval from a to b are equal. This means the function is a constant function. Therefore, f of x is a constant function. On the interval from a to b. Proved. Atom number D on the screen is actually a simple consequence of atom number C. Now proof. We let uppercase f of x be the difference between the two functions, f of x and g of x. And then it's because the two functions f of x and g of x are differentiable on the open interval from a to b. So the difference between the two functions is also differentiable on the interval from a to b. The uppercase f of x is differentiable on the open interval from a to b. because the derivative of the two functions are equal. The derivative of f is equal to the derivative of g for every x on the open interval from a to b. We have the derivative of uppercase f of x is certainly the derivative of f minus the derivative of g is equal to 0. This is true for every x on the open interval from a to b. If you look at the conclusion in atom number C, you see the two conditions are satisfied. The function is differentiable on the open interval from a to b, and the derivative of the function is equal to 0 at every number on the open interval. By C, uppercase f of x is a constant function. Say uppercase f of x is equal to the constant of c for every x on the open interval from a to b. This means, therefore, now we're going to replace uppercase f of x with the f of x minus g of x. Therefore, f of x minus g of x is equal to the constant of c, which means the two functions f of x and g of x, they differ by a constant of c. So f of x and the g of x differ by a constant on the open interval from a to b. So we have proved atom number D. Now using MVT, we can prove a fact we have been using over and over again. If the derivative of the function is greater than 0, is positive on some interval, then we want to prove the function is increasing on the interval. Now the proof. We choose two arbitrary numbers on the interval. Now let x1 and x2 be two arbitrary numbers on the interval from a to b with the we assume x1 is less than x2. To show the function is increasing, all we need is to show the value of the function at x1 is less than the value of the function at x2. To show that, we are going to apply MVT on the closed interval from x1 to x2. Before using MVT, we need to verify the two conditions. Now, since the function is differentiable, on the open interval from a to b, we have that the function is continuous on the closed interval from x1 to x2. Again, differentiability implies continuity, and differentiable on the open interval from x1 to x2. So we can see the two conditions associated with MVT are satisfied. Now we can apply MVT. By MVT, there is a number c on the open interval from x1 to x2, such that we use the second form of the equation, such that the value of the function at x2 minus the value of the function at x1 equals the derivative of the function at c and times x2 minus x1. Now, using the condition that the derivative of the function at any number is a positive number greater than 0. In particular, the derivative of the function at c is positive greater than 0. And of course, x2 minus x1 is positive. So we have the right-hand side is a number greater than 0. It's positive. Now, if x2 minus x1 is positive, thus the value of the function at x2 is greater than the value of the function at x1. Or the same thing, the value of the function at x1 is less than the value of the function at x2. This means that under the condition that x1 is less than x2, we can prove the value of the function at x1 is less than the value of the function at x2. This means the function is increasing. Therefore, the function f of x is increasing. On the open interval from a to b, we have proved item number E.